mis à disposition, vous avez vu tous que la conférence de la semaine passée est sur YouTube. Alors, il y a donc les transparents et la voix. La voix, on ne l'entend pas très bien, mais on entend quand même avec les casques et mettre dans les volumes. Je trouve que c'est très bien donc, de voir ça. Et aujourd'hui, tu vas faire la même chose. Donc.
Ah oui?
Super.
Okay, so I would today talk about the more practical part. So last time you've seen all the research, and now I'll show you which part of the research we were actually able to apply, which is, as usual, just a small percentage. But to put it a bit in perspective, so let me tell you about our course a little bit, what we're doing to try to make it more interesting, to flip the classroom, how we're structuring the homework. I think that's kind of interesting for everyone who gives homework, because we hit upon something that works really well. How we do the exams on the computer, and I'll talk a little bit about this MOOC that we did, and it has a fun story behind it, so I think you'll find it interesting. And if I have some extra time, I'm going to show something that has nothing to do with this, just because I need an audience for it. I'm writing a new electronic textbook, and there's some interactive materials in there that are pretty interesting, but only if I have time. All right, so our courses, we have, just like you have, two semesters of introduction. The only difference is we use Java, we use early objects, but that's just a minor thing. The content of the course of our CS1 is the same as your Inf1 pretty much. Control structures, algorithms. The only thing that we do different is that for some reason we put a little bit of object orientation in there, because when the course was developed 10-15 years ago, that was what everyone did. And it does us no good, but it also does no harm, so we're not really doing anything to change it. And the second course started out as a data structures course, and now more and more programming has moved into it. So this input-output at one point was file input was moved into because there wasn't space in the first course. Same thing with interfaces and inheritance, and then the rest is classic baby data structures with lists, sets, maps, and so on, and trees, but not balanced trees, and some informal Big O. So that's very much a typical two-semester course here, like you find it on any of hundreds of American universities with pretty much the same contents. So then the students go on to take a more serious course in data structures and algorithms, where they do balanced trees, graphs, more sophisticated algorithms, and of course formal Big O's, maybe a token proof or two. Then we kind of have two courses in software engineering. The first one is called Object-Oriented Design, and you may have noticed that we introduced interfaces and inheritance in CS1, which is pretty worthless actually, in CS2, and now we're doing it again in this CS3B course, and this time for me. And so I guess there is a spiral at work. We figured the first time around no one understands much about it. The second time they get enough so that they can work with the Java collections framework, which does require some knowledge of inheritance. And now the third time around we do it deeply. And then that part does work very well. So we do some design patterns, and we have the introduction to software engineering and the first team project. And then there's another course with much more software engineering, much more in depth. The other place where students see programming is in a course of programming languages. That course has the stated goal that no matter what else should happen, that students should have non-trivial programs in a functional language. And forever we've been trying to argue what is non-trivial, and I say at least a few hundred lines of code, and so hopefully that's the definition that sticks. And so what many instructors do is they make students write an interpreter and or a compiler in a functional language, so that the students actually get some experience under the belt. Now someone asked last time, what do we do about C? And so in the computer organization course, students learn a little bit about C and inline assembly, enough that they can put it to work, say, in an operating systems course. We don't really, unfortunately, have a course in embedded programming, but if they take it with the computer engineering department, then they would know enough C to succeed in that. So that's kind of the structure of where we do programming. Of course, we have other courses in operating systems and so on that I've not listed here. So the first thing that we do, that we did, and we've done this for forever, even before we used Java, is we've very explicitly said the goal of CS1 is not to teach Java. Java is a vehicle, just like C++ was a vehicle before, and before that C and Pascal were vehicles for instruction. And so we have a syllabus. That syllabus really has not changed too much over the many years. And so we teach just enough Java so that students can do what they need to do. So for example, we don't teach the do loop because they can use a while loop. We don't teach break. Obviously, you don't need break. Java without break is Turing complete. We don't teach continue or switch or any of a number of other more or less bizarre constructs that Java has, just to make sure that students don't really spend a lot of time dealing with these very gratuitous kind of constructs. Now, every once in a while, someone says, well, what if they later on, as they read real code, encounter one of these statements that we've never taught them? And 20 years ago, for us, that might have been a problem. But today we have an answer, and that's the students know Google. And so we're not concerned whether students know all of this language. We figure that they can Google just as much as the rest of us. It's not that they would have ever learned it otherwise anyway. They would have Googled one way or another. So this way we take out a bit of that. Another example is we don't use the character type. There's no particular reason to use the character type. You can just use strings of length 1. We use strings anyway for many, many assignments. And so there's the characters are strings of length 1. And so once in a while when we get a new instructor, they say, well, how can you not teach the character type? The characters are fundamental things. Well, we don't actually teach them about bits either. We give them integers and numbers, and the fact that they're made out of bits is not something that we're too concerned about. So we say strings are the fundamental type. It has operations on it. One of them is to extract the substring. Substrings of length 1 are characters. And that works great. It eliminates a whole bunch of confusion in the students' minds between what is the difference between a car and all of that kind of stuff, which is of no interest to us in the intro course. Another thing that we do that works really well is this would work in C++ as well, is arrays in most languages are really primitive. They are primitive in Java, they're primitive in C++, and students are not really amused by the fact that they're primitive. Like if you want to grow an array, you have to allocate a new one and shovel all the values over. Every language, with the exception of raw C maybe, has some way of dealing with that. In C++ you have vectors. In Python you have lists. In Java you have these things called array lists. And we just teach them as the fundamental way of storing stuff. And the fact that there is an underlying array, we do teach them because sometimes the syntax of the array is maybe a little more pleasant in Java. But in C++, when we taught C++ in the same way, we never taught C++ arrays. The only time that we mention is that you see them when you have command line options, and we immediately told students how to put them into a vector. There's no logic for doing that. So the syntax is more uniform with these constructions, and they're plainly much more useful. I do have one slide that says, when should you use an array? And the answer is when a computer science instructor makes it. And that seems to be a pretty good guide. Another thing is we do some inheritance, but inheritance gets messy when you get into things like superclass construction. And so we just don't do it. We just make sure the superclass has a no argument constructor, and so we don't get into those parts of the messy syntax. And we teach a tiny, tiny subset of the library. The Java library is humongous. No one would know it in its entirety. Now, I've written this thick series of books about it, and I don't know all of the library. So we don't see that as a goal of CS1. So the goal really is to simplify the language and focus on the algorithmic part that really should be at the heart of the course. And that's something that it doesn't matter what language you pick. I think those are always great goals. And the students love it, of course, because they're not held to task for accidental complexity. The students hate it because now they actually have to worry about the stuff that's really difficult. So we have, somewhat unfortunately, a format where students meet for 2 hours and 30 minutes every week in a large lecture hall, 2 sessions. So there's 150 to 200 students in this lecture hall. If the university would have a larger lecture hall, they would make us use it. But that's as large as they get where I teach. And so that's been where this interest in the flipped classroom comes in. So, flipping a classroom means trying to do something other than lecturing, like I said last week. And so we're trying this as hard as we can. By the way,
just a question.
Yeah.
How many weeks there are in the semester?
15.
15.
So it should be pretty much like here. So I just happened to notice that there was a workshop on flipped courses offered by someone here on February 4th. And I put a link up to that. So if you're interested in seeing what your peers have to say about flipping the classroom and lecturing less, that might be worth attending. So it's not just me. But I'm not on the intranet here, so I can't show you that. But click on it. I'll put the slides up, and you'll see when that workshop is offered. So the first thing that we do is we assign students pre-class reading. So we assume that they come to class with the basics of the textbook in their head. And we're not telling them anything about basic concepts. We don't tell them what a variable or what a loop is. We go right in and come up and try to discuss some of the more difficult things. So with a for loop, we might show them common errors or some of the less obvious ways of using them. And we do a lot of problem solving. Let's say it's not just me, so we have a set of instructors who teach this course, take turns. And so these are the things that we're all pretty comfortable doing. The live coding works well, where just to develop some more intricate problem, one works out in detail. And here's the problem statement, some attempts at solving it, involving the students, maybe with generating some ideas, and then doing the whole thing. So when I do this, I always record this activity, and then people can look up the movie later if they're interested in. And that's also something that's quite popular with the students. So the students like the fact that they see this problem solving in action, and they generally prefer that over going over the PowerPoints of standard constructs. As you'll see in a few slides, there is a very active homework discussion on Thursdays, and I'll show you how that comes about. And so we're trying to do some of these active learning exercises where I put up some slides. Let me see, I should have a sample here. Yeah, so here's like a good sample of something that I might put on there. And so this was 7 weeks into the semester. And the question is, how many times is the condition of this for loop evaluated? And so then I'll invite students to, we use a discussion system, and I make I just make a question in there. And so the discussion system that we use has a module for doing that. And then I can see in real time how many students have answered and who answered what. And so in this kind of situation, I almost know, because I've done it several times, I know I'm going to get the wrong answer. Most students are going to say, well, clearly 6 times. And so then that's interesting, right? Now one can talk to the students and say, hey, the condition was evaluated a 7th time, and then it failed. Right? Sure.
I equals I plus 2.
Ooh, oh yes, thank you. Yes, now I have to actually have to think. Oh God, yeah. So at this point I would just say, now I have to think, I don't have any idea. So I gave you the wrong question. So the original question that I had was where I equals I plus 1. Yes, thanks for catching that. And so that was the one that I meant to look up. I missed that. When it's I equals I plus 1, then it drives home to the student that the condition gets checked one more time. And so that's interesting. Now with I equals I plus 2, at this point here, I would say, gosh, I have no idea. And then I would start doing what I always do in this case and draw myself a little table and say, okay, I is 1. And that's exactly the kind of thing that I want the students to be able to do. And so what I can also then do is I can encourage the students, when I see what usually happens with a question like that, I see the students, they just kind of sit there, they try to scratch their head a little bit, and if after a minute no one has taken out a sheet of paper, then I can say, well, how about everyone take out a sheet of paper, and then I can later collect a few of those. And so one can use something like this as a hook to do something interactive that gets the students going. All right, so I usually do in a lecture about 3 to 6 of these, depending on what the material is. And at first, it's slow going. So one of my colleagues who we hired newly, she looked over my video that I took, and she said it was really painful to watch because I had made the first assignment, and I just did absolutely nothing for 7 minutes because for some reason the students were slow to get started. And so you really have to stick to it around the first couple of times you do that, and then the students realize that this isn't going to go away. And then they start participating much more quickly. It also helps that eventually they catch on to the fact that because of the nature of the discussion group that we're doing, everyone knows what everyone has done and who has answered and who hasn't answered the questions. But the first time they don't know that. So we try hard to do this, but it's very, very difficult. So when we hire a new person, it takes, I would say, a couple of semesters before they get out of lecture mode and before they can learn to be more interactive. And so one can't expect instant miracles, and one really has to do a lot of hand-holding there. And every time that I give a lecture, I'm still disappointed at the end of it how much I lectured and how little I took advantage of the things that I tell people that they should be doing. So pre-class reading, this is a total winner. You should do it. It is very easy. I typically assign about 3 sections from the textbook, and then I put a quiz into the learning management system. In my case, the publisher of the textbook has given a whole bunch of quizzes, and most of the questions are reasonable. And then I select 10 of them. You don't even pick the same ones year after year. It doesn't really matter. And so the questions are usually just dead easy. Like here's an example of one. Multiple choice. And so they're easy for us. And for the students, it's a bit of thinking. What typically happens, and so a colleague of me asked that, well, will students really first read the textbook and then go to the learning management system and do the quiz? Well, of course they don't. Of course what they do is they go and read the quiz, and then they read the minimum amount of stuff in the textbook that they need to answer the questions. But hey, they're reading. So that's fine. So one thing that you can do is include one hard question, like as question somewhere. Doesn't even have to be the last question. It can be the first or the third question. And then where most people are going to get it wrong, then you can take that as a discussion thing in the next class because people are somewhat interested in that. So sometimes what happens is we have a very active discussion group, and so I see that people are going back and forth about a particular question on the discussion group. And then I say, oh, that's great. Then I can talk about that in class. And then you have something to talk about and something to get the discussion going. Then I make a variation of that and ask that as a clicker question, and off I am to some active learning. So the other thing that you should definitely do, that is just so easy to do, and it's such a winner, is this thing that of 2 homework submissions. So we used to, a long time ago, we used to give homework 4 times a semester. And that was a terrible idea. So we would give these hard and involved and complicated assignments. And we would try to get the students to spend a few weeks with each of those assignments and then produce a wonderful solution. Unfortunately, students being students, almost none of them even looked at the assignment until 2 days before it was due. And then there was no way that they could produce a nice solution to a complex assignment in the amount of time that we gave. And so that was pretty obvious. And so what did they do? They cheated. They copied from each other, or they just did a very half-assed job. So we completely went away from that. And now we assign 3 problems per week. And each of them is fairly short. One should be very easy, one medium, one challenging, so that you engage different students at different levels. We give them starter code. We're not really fans of, in CS1, say that students should produce a program from scratch. For that matter, we're not really fans in CS2 or CS3 or the software engineering course that students should produce programs from scratch, because no one in real life produces programs from scratch, right? You always have to work with existing code. So there's value to work with existing code right from day one. So we give them some sort of code, and for the students it's less frustrating. They have something to look at. They hate looking at the blank screen, and I can see why. And now this is the kicker. We make them turn in a draft, a simplified version of the problem on Wednesday, and the final version on Sunday. And it's such a brilliant idea, because what happens is that on Wednesday, students being students, they say, oh, there's this draft due on Wednesday night. And then something amazing happens. They read the homework assignment 4 days before it's actually due. This has never happened to us until we introduced this. On Thursday, there are lots of questions, almost all of which are, what the heck am I supposed to do? Now they have 4 days where they can think about it, in the bus, in the bathroom, wherever, when they take a shower, as what it is that they're supposed to do. And so they actually have a fighting chance to finish the homework. And so this works totally wonderful. All the problems are auto-graded, so even if you think the final you don't want to auto-grade it, you can auto-grade the drafts. So I'll just give you a sample so you can see what one of them looks like. Let's see, yeah. So this happens somewhere when they've learned some arithmetic. So this is the French revolutionaries who want to get rid of nonsense such as monarchs and old-style measuring systems. And so they need to convert from the normal time, with 24 hours, into the French revolutionary time with 10 hours a day and a minute that's a thousandth of a day. And so then there's some starter code here that's given to them. There's a tester, a little unit tester. There's this thing. This is done in Java, so it's in the format of a class. But you could do this in C++ in the same way. We'll just arrange the code differently. And then the students fills in their things here, submits it to the autograder, and then they fuss with it for a while, and some stuff happens. So I'll talk about the autograder a little bit later. Right now, of course, it didn't do very well. So that's 1 out of 3 assignments that they would have gotten in that week. And typically it takes them not very long to do the starter thing, the draft, but it usually takes them a few hours to do the final versions, and they do really learn quite a bit from that. So that's where they get a lot of their just technical skills. So this all works because of great automation. So the entire idea is that you want to give lots of practice, just like a piano student would play a tune over and over again. We want students to do a lot of coding and do these tasks over and over again, so that some of the things become pretty automatic. And we want them to get instant feedback. And so the autograder cannot be beat with that. The student does a little bit of work, they instantly are told, well, that was stupid. But usually it's not so bad, because we give them small things, and they can, particularly with the drafts, and they can succeed to the point where the autograder says, good job. And then they move on to the next problem, and the autograder again goes through the same thing. So the fact that they have instant feedback is really useful for them, and they appreciate that greatly. It's much, much better than having to turn it in and get some grade back 2 weeks later, with some annotations here or there. Because 2 weeks later, many of the students don't quite remember what it is that they were even supposed to do. So instant feedback is great. It's just like what you have when learning just about any other thing that needs to be mechanical. You want to know right away, did you do a good job? So the trouble with autograders is there's been autograders for 30 years. The trouble that I find is that if you look at something like WebCat, for example, which is a very nice autograder. It's a very involved system. It has unit tests. It can make students write unit tests. You can write unit tests. It then grades it. It gives you histograms and whatever. But the trouble is, to prepare a problem for a fancy system like that takes a long time. So if you wanted to assign a homework assignment and then put it into a professional system like WebCat, you probably spend like a weekend for one problem. Well, if you assign 3 problems a week, and because you want to avoid cheating, you can't reuse the problems from the previous semester, you need something faster than that. And so that's where I designed this thing called CodeCheck. And so the idea of CodeCheck is, what if you want to have an autograder that is as simple as can possibly be, so that you can generate lots and lots of short problems. And you can generate new ones every semester, so that when the students try to Google or ask their friends for a solution for the homework, that they're overwhelmed with so many slightly different versions of the same problem that it is easy and faster to just solve the damn thing than it is to go through all of the Google results. So, so the idea of CodeCheck is must be so easy to produce solutions, problems and solutions and their variants, that students are just overwhelmed by what they find there, and they just stop doing that and just work on it. So I'll give a very brief demonstration of how CodeCheck works. So what you have to do is okay, so there's 2 directories. There's a solution directory. There's a student directory. Let me show you what's in the solution directory. In this case, there is fizzbuzz.cpp. So that's the solution that you would write anyway, because we are giving the solutions out to the students. We do want the students to know on Monday morning what we expected them to do, so we give them a reference solution. Now, many people don't do that because they say, well, what if students then use that solution to turn it in next semester? Well, that's why we give a different problem set next semester, so that we can give students a complete solution. And so since we have to write the solution to give them to the students, we might as well use the solution for grading. So let's see what we give the student. So we would give the student just a skeleton. So you see here, there's something for the students to get started, and then just a dot here. And of course, we give them a description of what they should do. This is FizzBuzz. Then we give him a couple of inputs. Here's one, and here is the other. So this is the file that contains 10, and then the file that contains 30. That's what you have to do to make CodeCheck happen. You zip up these 4 files and you upload them to CodeCheck, and you're done. So in fact, I could do that in real time. So here I've zipped them up, and let's see if I find a link to CodeCheck here. Nope. There we go. So this is the world's simplest user interface. So now CodeCheck has now taken this thing here, and now what you do is you give the students this URL. And you say, go here, and now the student just does their work here. In this case here, they did not achieve the actual output, and they have to try harder. So that's how CodeCheck works. Notice that the professor doesn't have to register for it. The student doesn't have to register for it. The professor just goes there, uploads the zip file, the student uses the magic URL, and that's the end of it. When the student is done, they can take this page, or there's actually a little downloadable file at the end that contains their results, and they can turn that into the learning management system. So I designed this so that there's no extra login required by anyone. I do realize that someone could use the system to mine bitcoins, but so far no one has done that. All right, so this has been a total winner. That it enabled us to do the 6 assignments per week, the 3 drafts and the 3 finals. The students absolutely love it. The instructors may not love it, but because it is work to come up with new problems all the time. But it is simple enough that everyone I've showed the system has used it. It now works in, it used to only work in Java, now it works in C, C++, Python, Scala, and Scheme. And so if you teach in any of these languages, I invite you to have a look at it. You can use it. You don't even have to tell me. You can just go to the URL and upload your problems, give your students. And no one will know anything about it.
What if you have multiple files
Oh, you zip them up. I mean, you can add in as many files as you want.
and the student that's
They get to see them all. So whatever you put into the student directory, the student gets to see. So you can put in, if you have like some library, you can add those files in there. If it's in Java, you just add a jar file. If it's in C++, they would see the source of it. You can hide them. You can make it so that they are there, but the student doesn't see them. Like we did this lab from our self class with students did some image processing in C or in C++, and so I just tossed in a file that reads the images, and the students didn't see it. So it's a pretty flexible system. If you have questions about it, contact me, and I'll be glad to evangelize it. So exams, we give 2 exams in class, 1 final that's a little longer. And so what we want to check in the exams is, can students code? We're not interested in whether they can give us the definitions of things or do multiple choice questions. All we want to know is can they code, and can they design a little bit to the degree that you can check that in this time frame. So it's all programming questions. We give them some starter code. They don't have a lot of time, so we have to give them most of the code. We say, can you complete this? Can you fix it? Can you trace it? There's a few skills that we want. So there's a couple of questions, one in a midterm, one in the final, where it says, here's some bad code, run it through the debugger, and just tell us what happens, and take a screen capture on the way, screen capture of this, a screen capture of that, and that way most of the students have no great trouble with that because they've learned the debugger in the lab. There's a few students who've skipped that lab, and then they see that was a bad idea. And that's exactly the message we want to drive home. So in CS2, we do that with a couple of the other skills that we want them to learn. We force them to give evidence through screenshot. Students upload it all to the learning management system. There's some paper submission that I always ask for, even though most of it is electronic, and that's mostly, for one thing, to encourage students to do things on paper, such as code tracing or making a sketch of, say, something geometric or a linked list or something, and also to reduce cheating. Because it is theoretically possible otherwise for someone not even to be in class and have a friend mail the URL, let's do some such thing. And so we've been worried about cheating, and it has in fact been a problem. So we have evidence that students have been cheating. Even though they're not supposed to use the internet, even that when we jammed the internet, then they would use their phones to communicate. In a large room, it's difficult to proctor completely. And so you do have to proctor vigilantly because the computer gives them this extra tool to make cheating harder to detect. And you don't have handwriting, it's easy to get files back and forth and all of that. So that's last semester. I did this thing that worked very well, but it's a lot of work, so I'm not sure I can recommend it as a universal solution. The trouble that we actually had is we didn't even have to jam the internet. The university did it for us, and the Wi-Fi worked very flakily in the room. So I said, okay, I'll give them an encrypted version of the exam the night before, and so that they could install it and have it on their computer, and then I would give them the key the next morning. Then I realized that, hey, if I'm decrypting it, I didn't want to use the encrypted zip files because I didn't think they were safe. So I wrote my little decryptor program. But if I'm decrypting it, I can personalize it at the instance of decryption. And so every student had a slightly different exam. And so the students, they're filed in. And you know how students are, they all want to sit in the back, and no one wants to sit in the front. And normally in an exam that makes you very nervous. And I said, ladies and gentlemen, sit all back there. You all have different exams. And so a groan went through the room, and it must have worked really well because the curve was a little different. And so I think so it would have been possible in theory for students to cheat, but it upped the ante dramatically. And much to my surprise, it did not slow down grading. I thought it would grading would be much harder, but if you have a rubric that is more concept-oriented than detail-oriented, you can look at the problem just fine and see what a particular student had done. And the variations are small. Some students had to draw a row of rectangles and circles that were interleaved. Some of them had to do a diagonal of diamonds and ellipses. And so the basic algorithmic idea was the same. The kind of mistakes that they could make were the same. But each problem was clearly theirs. So, so the exams with the computers are a win. They make the students practice the skills in an environment that they're familiar with, and it helps with the grading. And of course, the individualization that it does describe would be impossible to do without computers. So another thing that really works well for us, because we have these large lecture classes. If you have 200 students in a class, you want to get some kind of discussion going. And so they've had these discussion groups for a while. And this system, Piazza, has really done a great job with this. So this is some startup. And so they do this discussion group, and it looks like a discussion group when you see it here. This discussion, questions and answers and stuff. But what's amazing about it is to what degree these students are using it. So in this one semester that I got some sample, in 15 weeks there were 1,651 posts, 25,000 contributions, some of which were clicker answers. So maybe maybe half of them just came from clicker answers, but that's still a lot. I had to respond 206 times to questions, but get this, the students responded 2,156 times. And so they really have been helping each other. An average of 6 minutes between some question and some response. Whether that response was the correct answer is a good question. But so there's a lot of social interaction going. The students have done a good job helping each other. And so the question that comes up in an environment like that, is it actually okay for students to post code? Answer here, and some student posts code. And at first, I was worried about that. But I think I said that last time. If you have this many posts, there's so much bad code out there that for the students to figure out what's the bad code and what's the good code is actually not so easy. And in the process, they read code, which is hard to beat. So, and here you have a typical thing where someone made in a kind of beginner's error that over here they redeclared these things as local variables, and so the constructor never actually touched the instance fields, and some student then points that out. So this is not something that I have to point out. This is something where some other student reads through this. Let's see if I can get to this here. And here, so James says, yeah, this was done. And the good thing is later on when someone else makes the same mistake, and students being students, they don't always read through all of the questions and answers before they post theirs. Someone will say, see item 1644. And then the student, they get to learn something that's useful socially, namely how to deal with this stuff. That, unfortunately, only works when you have a large group of students. So if you have a class of 35, that doesn't work. For some reason, you don't have enough of them to have this momentum. But if you have 100, it starts working great. So what we do in classes where we have multiple small sections, we actually make an effort to have common homework so that we have a common discussion group. But this is something that is really useful for students. And like I said, there is a poll feature for clickers you can make. So I could make a new poll. Well, I'm not going to show it, but you make a new poll and you ask students 4 questions. And the questions that I ask them are A, B, C, and D, so that they just match the slide. I don't even bother to ask the questions. I just put a slide with the questions, like something like this. And then I would just copy and paste these answers. And that's the end of it. And so having the discussion and the poll together turned out to be a bit of a win. So check out Piazza. It's a very nice system. So far it's free. and really recommend it. So with the labs, we try to make these labs more interesting, and I think we're succeeding in that pretty well. In that, there's two things that we want to do. One is we want to have problems that are intrinsically somewhat fun. Like here, I saw this poster in a science museum where you can see that you can read text even if in every word 2 letters are different, and you can actually read it perfectly well. And so I thought, well, that's half of my life. I go to science museums and I ask which exhibits can I turn into something in the CS1 lab. And so that turned out to be a very easy lab, very popular with the students. The other thing that we're trying to do is to introduce practical skills that they might not otherwise learn. So in CS1, there's various labs where they have to do code tracing on paper, where they have to write pseudocode on paper, which they hate, where they have to analyze algorithms on paper, or interactively, maybe through some group discussion, where they have to discover new algorithms. So there's one lab where I bring in a bunch of Straddle pieces, and they have to use the Straddle pieces to visually demonstrate how they discover a new algorithm. That always works very well. We have other things, dominoes, playing cards for this kind of visual activity. It works, but it's a lot of training with the lab system. So in CS1, they have to learn how to use the debugger. There's a couple of labs. And in CS2, we crank up what they need to know about software tools, because we have the trouble that otherwise they would never learn it. And so it's again in a spiral fashion. We don't expect them to excel in it in CS2, but we want them to get started. So we want them to get reasonably good at the IDE, that they know things like auto-completion, refactoring, the API help, and that kind of stuff that makes an IDE worthwhile. We want them to learn the command shell. So this was controversial about 10 years ago, but nowadays all the colleagues have realized that when you access that computer out there in the cloud, that computer does not run a Windows user interface. So students do have to learn the command shell. We start that in CS2. They have to write some simple scripts. We get going with version control at a very basic level, and so that's my my next fight when I come back home to extend that into the CS3 course in a spiral way. There's a little bit about unit testing, and we crank up the use of the debugger. So, for example, there's a lab where they have some broken code with one with linked lists, one with trees, and they actually have to draw the nodes, write the hex addresses next to them, and do the kind of thing that you wish that your students would do. But they do. It's not a very popular exercise, but it's useful. It's the kind of thing that you can do really nicely in a lab. So, and we keep tinkering with these labs because it's kind of fun to do. And if you have the same lab semester after semester, you again have the problem that students turn in the same stuff. So we do feel that we need to keep evolving them. A couple of minor things about course management. Cheating is unfortunately a big problem. I wish it wasn't, but the lowest 10% probably cheats tremendously. And so there's a plagiarism checker that we use. And to get the students to at least think before they do this, so the plagiarism detector gives a run of what are all of the related programs that look like suspiciously similar. And in week 3, I always accidentally publish a run with real names. And then I profusely apologize and take it back. Of course, then everyone looks really closely to see who it was who wrote those suspiciously similar solutions. And it puts a stop to it for a few weeks until they start. The other thing that we're trying to do is we're trying to identify the weakest students before it's too late. And well, when is it too late? In week 4, it's too late. So a student who has not done anything up till week 4 and just let things slide, they turn in the homework, they can't catch up from week 5. It's just not possible. The loops start and they're just totally lost. So we try very hard to get everyone who looks like they're going to be struggling in the course to know who they are, to have them in front of a tutor by week 4. And so the way we do this, we have all these quizzes and all of the stuff in the learning management system. And so we wrote a little, we can script our learning management system, fortunately. So we wrote a script that gets run twice a week that identifies the 20% weakest students just by some metric. And we send them an automatic email that says, hey, have you considered seeing a mentor? that gets more stridently worded. Hey, you should be really seeing a mentor in week 2, and hey, you're a fool for not having seen a mentor yet in week 3. And so we do that, and that's been pretty effective. It turns out it really is necessary to track whether the students really do show up, and otherwise, the phone calls that you have to make. So we have a student body where with the weakest ones, we have to make that effort, and without automation, it all wouldn't work. But with automation, you can get a handle to it. So I want to tell really briefly the story of this MOOC. So you all know what a MOOC is. It's a massively, I don't know what a MOOC is, massively open online course. Yes. So the people who you see here is our university president, the provost at the time, a venture capitalist, Mark Andreessen, the creator of Netscape, by the way, and Sebastian Strand, the CEO of Udacity. So these people met in January 2013 and had a great idea, namely that San Jose State should be the first university in the world to open a 4-credit MOOC, meaning a college course that you can take through this MOOC platform. And so the subjects that they picked were remedial math, statistics, psychology, and CS1. And they did that because the university president said, these are our problem courses. These are courses where a lot of students are having a hard time, except for CS1. CS1 was in there because I said, I want to know how to make a MOOC. And so I put myself in there as well. And it was a complete and abject failure. So it turns out that if you want to help students to get better at remedial math or statistics, you do not want them to do this online. They're going to do worse, much worse than they would do in a classroom. But in CS1, it turns out it was okay. They didn't do any better than the classroom, but they didn't really do any worse. So, and what happens, of course, is it pre-selected those people who kind of thrive in that online environment. So we use that material now for flipping courses. We tell students, work through the stuff, and then come to class having done some of these activities. And that's not a bad material for that, because I'm glad it's there. But what I really want to talk about is how, when you make information available in this format, how it completely changes how you deliver it. So my original idea was I would be talking for 15 minutes, they would record me, and then I would ask a multiple choice question. And so the Udacity people said, no way. They said, if you've talked for more than 120 seconds without asking a question of the student, you have failed. And so every time the clock was ticking, and if after 120 seconds I had not asked a question of the students, they would can that segment and record it over. And so it completely changes how you lecture. And in really, in a good way. Because it used to be that I would tell students what to do. You must use this construct in this case. But now, I can ask them. I can always ask, make them do something instead of telling them. So don't tell, ask is the thing. And in class, you can't do it because you only have 45 minutes or 75 minutes, and it would just take forever. But in this virtual environment, it doesn't matter. Time is of no importance. You can ask a question every 2 minutes, and if it takes the students to answer 15 minutes to answer each of the questions, it's not your problem. Maybe it's their problem, but it's not your problem. And so you can ask a lot of questions. And so that was really, really enjoyable to do that. So check out, I gave a link here, but my internet connection is too slow now to actually play the movie. But check out a couple of those lectures, just so that you see what that flow looks like. Almost all of the questions, once it went past the first couple of lectures, almost all of the questions are autograder questions, where I say, now you've listened to this, solve this puzzle with this code. And it was generally well received. So students like the format as something that kind of teaches them the basics. They do, of course, realize that in that format, all they learn is the basics. And it's not really a replacement for a college course. So, okay, I'm not going to talk about graphics, but I'll give some demo if someone wants it. I want to show off one more thing, just because it's fun. And so there's a lot of research on how to do other stuff that's not programming in an interactive way. And most of the things that people try hasn't really worked that well, because it's mostly, it shows students like an animation. Like you've seen all these sorting animations. Here I have one. And at this point, you've already lost all your students. So you might as well not do it. I'm serious. So when writing the latest version of my textbook, I looked around what people were doing, and so I did something that's interesting, and you can also put it like in labs and stuff. So here's an example. So I want to teach how the algorithm works for finding the maximum. So you have, it's a video game. You have 3 buttons. Next input, meaning you want to see the next input. Store what you've seen as the largest, and you're done. What do you want to do next? Oh, you want to see an input, right? What do you want to do? Yeah, so this was a bad run because that's not going to be a much larger one. Right? So we stored as the next input. We're going to store, no, sorry, next. Oops. And now I made a mistake. I should have said done. So it says try again. And I can try again. So I've shown it to you here where it's in isolation. How it really is packaged is inside a book. So here you see the regular textbook, and here's like the algorithm for maximum and minimum. This one is for an array. And so as students can read the book, they do this here. Here it's in an array. And okay, that's the largest. Let's see the next one. Okay, that's larger. Is that larger? Nope. And done. And I tell you, after having done this 5 times, you will never forget this algorithm. So I have a whole bunch of other algorithms that are done in the same way. There's other activities that are more mundane, such as tracing code. The kind of thing that you always want your students to be able to do. So here the students need to answer questions like, what is the next line? It's this one here. And what is the new value of whatever has changed here? So I think this is a G. And so on. And so this is an interactive thing. When you're all done, you're going to get something that says you've made 0 errors or 1 error or whatever. So these are kind of interactive activities that lend themselves to labs, to textbooks, and so on. And they all play on the same kind of theme that I've been trying to talk about all along, and that is to let the students do the work, to make them discover their things instead of you doing that. Okay. Now if I could find my slides again. Okay, I managed to lose my slides. That's a good sign for me to stop talking. Okay, one of you has erased my slides. No, here they are. All right, so the 5 things that I want you to think about is lecture less, make context interesting, make everything simpler, love the spiral, meaning treat something lightly the first time, then more the second time, then maybe a third time, and practice makes perfect. Put the students in a position where they do lots of repetitive things, particularly when it comes to CS1. In more advanced courses it's different, but for CS1 practice really does make perfect. That's all I got. Thank you.
Now question, discussion. Question.
About the spiral?
Yeah.
How do you organize the division and the redundancy between different lectures, the different courses?
Through the curriculum construction process, the curriculum committee, and so there's one committee that deals with the programming courses, and so then it's pretty easy to do it. If you have something that goes across areas, like with the C and assembly, that was trickier because the programming people and the hardware and operating system people all had to come to an agreement. But yeah, you have to come to an agreement with other people as to where to put bits and pieces of the material. And in theory, everyone buys into the concept, and it's just sometimes a little hard to come up with. and usually someone has to volunteer like a couple of hours or something.
Moi, j'ai des questions aux profs de programmation chez nous. Ça, c'est une approche qui est vraiment très différente. C'est très différente et c'est une approche. Là, moi, ce qui m'impressionne, c'est le volume des cours qui est vraiment beaucoup plus petit que les volumes que nous avons. Et apparemment, avec de bons résultats, parce que je pense que les étudiants, à la fin de ces cours, apprennent à programmer, quand même, j'ai l'impression. Pour quelles raisons nous avons besoin de beaucoup plus de volume et pour quelles raisons ce type de choses ne marcherait pas chez nous? Où est-ce que ça pourrait marcher chez nous? J'avais ces questions à René, à Guy Michel, à Olivier, à Marcel, qui sont des personnes qui enseignent à Eric, qui enseignent la programmation chez nous.
C'est difficile à répondre quand même, parce que on va exposer, hein, il y a beaucoup plus encore. Il faut avoir des outils pour faire pratiquer des choses, c'est très intéressant. Moi, je suis un peu horrifié de voir qu'on simplifie tout. Alors, si c'est dans le cadre d'une progression, d'accord, si c'est dans le cadre de prendre des spécialistes innovants, ça m'intéresse pas. Bon, ça va amener de bonnes choses. Hein. De pouvoir traiter certains éléments, ça c'est indicatif, hein, à voir, hein, pour travailler le problème, c'est là, je suis un peu indicatif. Quand je suis docteur, je vois que je suis un spécialiste, par exemple. J'entends des ingénieurs, c'est pas une critique, hein, mais qui ne sont pas spécialisés en informatique, qui font l'informatique à côté de leur travail. Je pense qu'effectivement, c'est des éléments qu'on ne connaisse pas, c'est bien grave, il faut pouvoir vivre. Mais si on forme des ingénieurs en informatique qui sont spécialisés, ils doivent connaître pas d'autres outils, des outils à disposition pour prendre du code aussi adapté que possible à la situation.
Mais je pense que là, les écoles américaines forment aussi des spécialistes. Là, c'est quand même des ingénieurs informatiques qui forment quand même, non? C'est les ingénieurs qui créent la plupart des outils que la plupart des programmes que nous utilisons dans la vie courante. Peut-être c'est à cause de ça que Windows se plante tout le temps, je sais pas. Mais c'est pas le cas avec macOS, qui se plante jamais. Je sais pas, mais là, tu vas pas me dire que là, ça ne forme pas les spécialistes en programmation. Et là, il y a une chose aussi, c'est que là, les choses qu'on n'étudie pas, c'est des choses qu'on peut apprendre ça très rapidement sur un site web, sur un bouquin, dans un livre, je ne sais pas. Est-ce que c'est pas plus important de connaître les bases, vraiment ce qui est important dans la programmation et les choses qui sont secondaires qu'on peut apprendre tout seul rapidement en consultant un site web ou un bouquin? En tout cas,
Yeah,
moi je
of
suis
course, I would
impressionné.
like to say it's not that we're teaching less. We're teaching, in the CS1 course, we're teaching different things. We have a much bigger algorithmic focus.
Yeah, but what's that the doodle? Is this something that you take over afterwards, that the people would have a chance to study and to practice?
What if they never do?
Then at the end of the courses, they don't know.
What if they graduate and they don't know what to do? I mean, life will go on. But if they graduate and they don't know how to find the longest sequence of repeating values in an array, then we have a problem. That is a problem we used to have. So it used to be that we graduated students who knew all of the syntax of a language, but they were very poor in solving algorithmic problems.
All the items that it shows not to display, and to teach how to do it, chapters and stuff, it means that potentially they don't know if it exists.
They might not. And there's many other things that they don't know that exist. And so you have to pick a balance. And so if I have to say, like when I looked at the Int1 course here, there's some algorithmic parts that we think are absolutely essential that the student has to be able to do, not just know, but to rapidly do. And that I can't imagine that the students here would be able to. They would learn it in a later course, but we think that that the higher value parts are algorithmic problem solving, and that is very difficult, and we want to make as much room for those activities as possible. And we would be very disappointed if the student later, after in year 3 or 4, cannot actually learn what a to-loop is or what the car type is from the many other things that we've told. So we do not think that we train a Java programmer, we think that we train a computer scientist, and hopefully they can learn everything that there is to know about language. After all, there are many other things about the language. Like you teach C++, you're not teaching them all C++. You've made a choice. And whatever that choice is, I had talked about that with Marcel today, and like when we were teaching C++ before we moved to Java, we taught the string class. That would be inconceivable to get a freshman, get someone out of CS1 who is not comfortable with using string conjectures. And so, he was talking about the final that he was laboring on, and turns out that one can't expect your students to be that familiar with it. So everyone has to make choices. And so what I'm saying is make the choices so that you have lots of time for algorithmic issues. The more you can throw away the syntax and save that until later or have students pick it up on their own, the more time you have for algorithms. And that really is what computer science is about. It's not about the syntax of the particular language.
But you talked about the syntax, right?
Well, do is a simple syntax, right?
Oh, okay.
Do is pure syntax.
But talking about the tools that you use or that you provide to the students to practice on a regular basis, including at home, yeah, it's pretty interesting to see.
Right.
That's the question.
Yeah, so that practice makes perfect. That is something that I strongly believe in. And it's really, it's easy to implement. The students will enjoy it because they enjoy, gradually getting better at it. It removes a lot of their frustration, particularly the weaker ones. With the strong students, it doesn't matter what you do; they're going to succeed anyway. But with the not so strong students, I think they will appreciate the practice and the guidance. Ours certainly do.
How much do you evaluate is the time they need to spend at home compared to the time they spend in lectures, and what is the total workload they have for a week?
I have to look it up, but I can do it with some precision because the students asked that very same question. And so we have a government formula for this. And so this is actually something that I put on this sheet at the beginning of the semester. Time spent. All right. So it's a 4-unit course. That means they should spend 180 hours per semester or 12 hours per week on this class. This always comes as a shock to them, but they do actually end up spending about that time. So of that time is 2.5 hours lectures, 2.5 hours lab, that's 5 hours. So we expect them to have 7 hours that they spend either on themselves or in study groups or with a tutor or mentor on preparing for exams and mostly doing the homework. So in fact, if I were to design a course that is a 4-credit course that does not ask the students to do this amount of work, I would be violating the law. So the American courses are definitely structured in such a way that students have a substantial amount of external time. Whether they really always do that, that is a great question. So when I look at the students who take a psychology course, I would be stunned if this can happen. But maybe in French, they spend more than that. I have the results are not to do with college.
But something I want to add is the reason I have about the training that we provide to the students is not a selfish exercise. It's much more as a provider for the next training we are going to because we need to have some computer exposure, some competency for computers. So if the next trainings that we send our students to, the teacher says, yeah, this is the level we want and this is the level that we can agree to have. According that maybe we take off some hours and so on.
it would be difficult to translate because of the language, right? That much of your exam was C minutia.
We can pick up a sample of how you just leave it.
And so it would actually, that's something we discussed when I looked at your exam, that it's always a good idea when you have a final exam for a CS1 course, if the contents of the exam would survive the translation from Java to C++ or from C++ to Java. Right? So if you take your exam and you take all of the questions and you translate them into Java, and the exam still asks meaningful questions, then I would say that means that it was a good CS1 exam. If I take my exam and translate it all to Python and it all works, then it would be a good exam. Now, I tried that with your exam, and there were many questions that I found would not have passed that test.
Oh, I thought we were about translation. Much more.
That was the translation that I think is the important one, not the English French. No, the question is, is CS1 is it a course in a particular language and it's minutia, or is CS1 a course into programming and algorithms? And so I believe strongly that it's the latter. And so when you're taking the CS1 exam, my feeling is, of course you have to have it in a particular language, but you should be able to take it and translate it into another language and have the essence of the exam survive. Yeah.
Je reviens un petit peu sur la question qu'avait posée Eduardo au départ. Moi j'aime bien l'idée en fait dans un cours de programmation de départ, premier cours de programmation, de simplifier au maximum. Maintenant, par exemple, ce serait le cas en première année d'école ici. Maintenant, en troisième année, quand tout à coup on doit enseigner des choses plus techniques, comme par exemple Hibernate, Java, des choses comme ça, des cours pour lesquels on est confronté à utiliser des syntaxes qui vont un peu plus loin. Alors, ma question, c'est à un moment donné, il y a un gap à combler. Est-ce que entre le cours de programmation de base et le cours de dernier niveau technique, est-ce qu'il y a un gap qui est comblé quelque part sur la syntaxe, ou bien est-ce que ce sont les professeurs qui enseignent par exemple à Hibernate qui doivent être très au courant des limitations du cours de base et qui les complètent, et ils font en sorte de programmer simplement sans utiliser par exemple des breaks ou des choses. C'est vrai qu'on peut faire ça. Hein.
Okay, so yeah, I can answer that with an example. So when I teach, say, the software engineering course, and so in recent years, most of our projects were with mobile development. And so it became necessary for the students to, within a few weeks, learn either JavaScript if they use something like PhoneGap, or Objective-C. So we expect our students, when they are in their 8th semester, to be able to pick a whole new language in a couple of weeks. We think that is a reasonable thing that they need to be able, and be reasonably productive in it so that they can take sample code that they grab from somewhere, and they actually integrate that into their project. That's an order of magnitude harder than figuring out what break is. So I don't think it's, if students, if that's something that you're worried about, you're not worrying about enough. Because in reality, almost everything that one does these days involves some other language, some other tool that the students haven't seen. And we feel it's our job to teach the students to learn more effectively. And so we actually take great pride in not teaching them everything in a mid-level course, but instead to work them through a process on how they can teach themselves. So for example, in the software engineering course, I make it a point that students have to ask questions on Stack Overflow. They get points for asking some questions. And I make it a point of having each team work out some technology pretty much on their own, with guidance from me, but where I'm not telling them every step, because that's something that these days everyone has to learn in order to function as a software engineer. The technology we use today is not what they're going to be using in 10 years. And so we figured that more of those skills and fewer facts is a better mix for a graduating student than try to teach them today's facts, but maybe not the skills that they need to keep learning. And so we really spend a good amount of time on trying to teach them how to learn. To say, okay, I know this much, what can I do? What kind of experiment could I run? What kind of starter code could I use to get to the next step? And I think that's paying off. Right now we're having this thing that students need to work in the cloud. and they don't really know. They have to. We don't actually teach courses. There is one course in cloud computing, but not enough to have them do an actual project. And because the students have learned how to learn, we were able to integrate some of that pretty quickly into software engineering projects. So I really don't think that it's the job to teach a lot of factual material anymore in computer science. That was, it's impossible. Everything that you learn today, it's going to be obsolete so quickly that really it's our job to teach the students to deal with that challenge, with that information overload, more than contribute to it.
Okay, this is a very important point. So you suppose your 30 years students should be able to learn a new language in 2 weeks?
Or to the degree that they can write, some simple programs and download the sample that does 80% of what they need and have it, yeah. I mean, how else are they going to pull down a job? I mean, the very first thing that any new student, the first thing that they get to do on the job is to do some maintenance on some project that they have never seen before. If they're lucky with the language, that thing. But the very first thing that they usually have to do is check out some code base, fix a few bugs. And if we don't get them to the point where they can't do that, that's not very good. 20 years ago, it was different. 20 years ago, most of the students who we graduated became like network administrators or technical support people. But all those jobs are now in Bangalore. And so we can no longer prepare people for that kind of job. And so we have to work on it. Not yet. I mean, that is a realistic. That's why we teach them, 3-4 semesters of programming, CS1, CS2, the object-oriented design, and the programming languages. And we hope that after that they can indeed learn the basics of a new language.
Okay.
Nos étudiants ils sont capables de le faire. Moi, dans mon cours d'AWS, j'aurais fait utiliser tous les containers de la standard library sans les présenter. Je leur ai présenté du code avec des expressions lambda qu'on ne donnait plus. Là, j'aurais expliqué, mais je veux dire, on peut après avoir des connaissances lacunaires, mais c'est pas grave, parce que c'est complète. Ils nagent un petit peu au début et puis ils s'apprennent. C'est pas. Ça ne change pas qu'ils aient des connaissances lacunaires. De toute façon, ils ont des connaissances lacunaires.
Finalement, c'est un principe qui s'applique à tous les cours. Moi, j'ai aussi réalisé, on a toujours l'impression qu'on doit donner des connaissances encyclopédiques. On a envie de présenter tout comme ça ils connaissent tout, mais ils n'ont pas pratiqué. Finalement, ils n'ont rien appris parce que c'est nous qui avons présenté, mais eux, ils n'ont pas travaillé. On a tous appris dans les cours pédagogiques, ce sont les étudiants qui ont travaillé, qui doivent faire le travail. Mais on a peur de les exposer à des choses qu'ils n'ont pas entendues. Et finalement, les choses ont changé parce que tout le monde fait tout tout le temps. Donc, quand on commence un nouveau projet, voilà, on a des nouvelles technologies qu'on doit apprendre. Et les étudiants doivent aussi apprendre ça. Donc, je crois que ça applique à tous les cours. Si un discours, j'aimerais bien réaliser des trucs comme ça, mais pour les réseaux, il n'y a pas de recours.
Et je crois que dans le domaine c'est inévitable de ne pas être encyclopédique, puisque c'est un domaine qui croît à une vitesse incroyable. C'est absolument impossible. Moi, j'ai compris tout ça parce que ça m'avait beaucoup frappé quand on faisait les nouveaux plans d'études. On avait listé toutes les choses qu'on devait voir dans un plan d'études informatique et de communication. Et on devait donner des priorités. Et on avait regardé que tous les points qui étaient à priorité 1, il fallait 5 ans pour les voir. 5 ans pour voir tout. Ça montre bien que c'est absolument impossible de tout apprendre. Mais ce n'est pas seulement les choses à priorité 1, c'est aussi les choses à priorité 2 et à priorité 3 qu'on doit voir. Et en 3 ans, c'est absolument impossible. Et que nous devons enseigner à apprendre, pas enseigner. On ne doit pas être les encyclopédies, on doit apprendre à apprendre. On doit donner vraiment des bases qui vont permettre à nos ingénieurs ensuite d'aller par eux-mêmes, de trouver des choses qu'il a été impossible de voir. Et là, donc, en ingénieur, tu sais, avec la vitesse des changements dans l'informatique, un ingénieur sort de chez nous. Et 2 ans après, il y a une chose complètement nouvelle qui sort qu'il n'a pas appris à l'école. Alors, c'est inévitable qu'il faut qu'il apprenne par lui-même. C'est absolument inévitable. Si on était dans les maths ou dans un autre domaine, je ne sais pas, dans l'économie où les choses sont beaucoup plus bien. Sinon, on pourrait être plus encyclopédique, mais dans le domaine.
Surtout, moi j'aime beaucoup l'idée de l'orthographe là, parce qu'il reste beaucoup de problèmes. Premièrement, ce sont les étudiants qui travaillent. Et on parle de la programmation, vraiment, on parle de la programmation des étudiants en cours. Deuxièmement, ils ont un feedback immédiat. Ils n'ont pas besoin, comme actuellement, ils font le labo, ensuite on fait des corrections pendant 2 semaines, et 2 semaines après, ils ont le recherche et ils ont bien fait le labo ou non. Donc ça s'applique aussi à tous les cours. Et troisièmement, pour le prof, là, on n'a pas besoin de se taper 50 fois le même code, de regarder s'il a fait bien ou non. Donc c'est quand même, je trouve que c'est un système fantastique, parce que les motivants, ils essayent de tester, ils tapent leur code, et tout de suite ils savent, ah moi là j'ai fait une erreur, et je peux corriger ça.
Vous regardez quand même le code, non?
Il disait que les assistants